All right, welcome class. Here we are, lecture 15, moving right along. And we find ourselves in a position to keep considering questions of mass equilibrium. So we started talking about last time that we have in the dilute limit a way of formalizing the chemical potential for a set of particles that are non-interacting, and from that deduce a couple well-known chemistry results, law of mass action, things like Henry's law, etc. We're going to briefly review those results before we start tackling a question of how particles will distribute themselves really between phases when we're out of that dilute regime, when we're actually thinking about converting a whole system from one phase to another. So today's lecture will be predominantly on the thermodynamics of such processes and pointing out some of the potential difficulties that thermodynamics has in considering phase transitions. That will put us in a position in a couple lectures to then be able to develop a statistical mechanics of phase transitions, a real microscopic perspective on these behaviors. But to start, let's go ahead and reflect on where we've been. So last lecture, we reconsidered our set of n classical non-interacting particles. This is a set of particles we're imagining at some high temperature, maybe a room temperature, so we don't have to worry about the quantum statistics that they obey. And they're sufficiently dilute or at low density that we can neglect their interactions. And under such conditions, the canonical partition function, we argued, so that at fixed temperature, volume, and number of particles, can be written as a product of V in some resolution lambda to the n that manifests the different spatial states that a given particle can be in, times a factor q int raised to the n divided by n factorial. That q int counted up with a Boltzmann weighted sum the thermally accessible internal states of our molecule. Things like rotations, vibrations, etc. To be contrasted with this, which again is the number of translational states, where we count those in resolution of that thermal wavelength lambda. From this, taking the appropriate derivative of log q, in this case with respect to n, we arrived at the ideal form for the chemical potential. That form, satisfied again for very low density, rho, denoting the density, is given by a sum of two pieces. So mu is equal to a factor that is linear in the logarithm of the density, which can be referenced to some scale, rho naught. That scale then determines a standard state chemical potential, or an offset that has information about the internal states of the molecule, or say the surrounding states of a solvent that that molecule is embedded in. So we could call this rho naught a standard state. And the associated mu naught to that standard state. Again, if rho is equal to rho naught, then mu is just mu naught. This is then the standard state chemical potential. And we discussed that this form underpins a lot of mass equilibrium that you learn in general chemistry class. For example, if we imagined a solution in contact with its vapor, so we have a liquid down there, a vapor up there, and there are solutes that can be, they're volatile, so they can either be in the liquid or the vapor, and thus can exchange between those two states. We found that solutes will partition themselves between the liquid and the vapor. In such a way that their chemical potentials in the liquid and the vapor are the same. That's the condition of mass equilibrium. That would be the point at which the concentrations of the solutes in the liquid and the vapor are no longer changing under conditions where the solutes are dilute in both the liquid and the vapor. That condition leads to, through that ideal form of the chemical potential, a ratio of rho L to rho V, the density of solutes in liquid to the density of solutes in the vapor, which is equal to e to the minus beta delta mu at that standard state. And this is what is typically referred to as the Henry's law constant. That's a question of solubility. We also considered a question of chemical reactions. For example, some molecule B, which can transition into some set of molecules C and D. The condition for mass equilibrium we worked out last time was that B times the chemical potential of B must be equal to C times the chemical potential for C times D times the chemical potential for D. If all those molecules are dilute, say this reaction is happening in solution and the concentrations of B, C, and D are all small, then we found that this equilibrium constant, this ratio of concentrations of B, C, and D raised to their appropriate stoichiometric power had a simple, satisfied a simple equality depending on that standard state. And those chemical potentials, in this case of the reaction. Let me give myself a little room and clean that up. So rho C times rho D to the C and D, that gives me units of must be positive minus B. Then I have some standard state chemical potential of that reaction. And this is indeed just what we normally see in chemistry as an equilibrium constant. And last time we talked a little bit about how one would generalize this away from conditions of dilute solutions, invoking things called activities. And we also illustrated molecularly that those standard state chemical potentials really reflect the reversible work to do that transformation at that standard state density. So under conditions where the molecules are dilute, I can actually envision doing a mechanical measurement, pushing molecules together such that they react. If I do that reversibly, I could actually predict from that measurement the solubility parameters or the equilibrium constants associated with some reaction. Okay, so that's contact with chemistry. I want to move on now to begin our discussion about how molecules or particles in general partition themselves between phases. So not in some dilute solution. So let's first consider the basic statements that have to be true for two phases to coexist. So let's imagine for concreteness, I have two phases, alpha and beta. So let's say that alpha is up here, beta is down there. For concreteness, this could be, say, liquid and vapor. It could be water and oil. Could be ice and liquid water. There are two phases that are distinct potentially in chemical composition as well as physical properties. For that state, if I was to look at my beaker and find two coexisting phases, a sharp interface between them, for that state to be stable and unchanging in time, a number of conditions have to be satisfied. In order for there to be no net energy transfer between alpha and beta, it must be the case that the temperature of phase alpha is equal to the temperature of phase beta. For the volumes to not be changing, it must be that the pressure of phase alpha be equal to the pressure of phase beta. Finally, each species that make up the potentially mixed state of alpha or beta, for there to be no net mass flux between alpha and beta, it must be the case that the chemical potential in alpha for each species I be equal to the chemical potential of phase beta for each of those species. That will ensure that this state is stable, unchanging in time. So that's a specific case, a specific two-phase equilibrium between alpha and beta, and the conditions that those two phases have to satisfy. Can we generalize this argument? You know, for example, that in water's phase diagram, there is a point, a temperature and pressure at which 3 phases coexist. What sorts of general thermodynamic statements can we make regarding the constraints that a set of phases with a set of chemical compounds, set of chemical species have to obey for that state to be stable? So let's generalize this through an example. It's an example of scenario you all maybe have found yourself in. Imagine you have a friend who really likes cleverly bartended layered drinks, you know, those sorts of shots you might once upon a time have been able to get in your favorite bar, which has lots of layers. You know, I am not a particularly fast bartender. I'm slow and take my time. So if I was mixing your drink and you might ask, for example, given my slow bartending abilities, how many layers would be possible for me to make? If I have some amount of different chemical species that I could add to this cocktail, and I mix it very slowly, so I have to assume that the endpoint has to be thermodynamically stable. I can't leverage fast abilities, the kinetics, to help me out. How many layers would be possible given some set number of chemical compounds, chemical species? This is maybe away from the bar, the case of the slow soda jerk. So putting it in pictures, let's imagine I have some phase 1, another phase 2, another phase 3. Maybe this one has some noticeable solutes. Maybe this one is more opaque. Let's give some colors to these. And now let's ask that under the case where I have R different chemical species, and I have V, not to be confused with nu, V different phases or layers, the question we want to pose is how many layers are thermodynamically stable? If I was creating this layered shot and I'm slow, given I have R different chemical species to put in your cocktail, how many V layers can I stabilize? Put in our terms of our 220A class, given R different components, how many V phases can coexist at one time? All right, let's define some things. Let xi alpha be the mole fraction of phase alpha and species I. So each one of these layers has some fraction of species I in the alpha phase. And let's normalize that such that if I sum overall I within each phase, I get 1. That means I need to sum over all R components. So if these layers, if these phases are going to be thermodynamically stable, that means that they have to satisfy a number of thermodynamic constraints. So I'll go to a new page. So the conditions for equilibrium in this system, well, again, for there to be no energy flow, it means that the temperature of phase 1 has to be equal to the temperature of phase 2, all of which have to be equal to for all V phases, if I have V layers. Similarly, for there to be no volume flow, the pressure of phase 1 has to be equal to the pressure of phase 2, has to be equal for all V phases. And the chemical potential for species 1 in phase 1 has to be equal to the chemical potential for species 1 in phase 2. Otherwise, species 1 would flow or repartition. And that has to be true for all R components. So species R in phase 1, its chemical potential has to be equal to the chemical potential of species R in phase 2, all the way up for the V phases that R can partition itself in. So that's a set of equations, a set of constraints or equalities that have to be satisfied for the system to be equilibrium. So how many equations do we have? Well, I have V minus 1 equalities along a row, and I have 2 plus R equalities along the top, or along the columns. 2 coming from temperature and pressure, and then each R component has its own set of chemical potential equalities. Now, what can we imagine controlling? What are the free parameters in this system? Well, I have the temperature. I can imagine heating this drink up or cooling it. The pressure, maybe I can do this under a pressure cooker. Does that work? Or maybe the analogy is breaking down. In principle, you can imagine for phases, I can control the pressure, and I can control free parameters that will distribute themselves are the mole fractions for each phase. So that is V. So each phase has some set of mole fractions. I have 2 plus R minus 1, because I have R minus 1 free mole fractions. And I have 2 for the temperature and the pressure. So those are the variables in the system, the pressures, temperatures, and chemical and mole fractions for each phase. So then how many free parameters do I have? So this is the number of variables, this is the number of equations, so I have some number of free parameters. So F must be equal to V times 2 plus R minus 1, that's the number of variables, number of equations, V minus 1 times 2 plus R. That gives me altogether 2 plus R minus V. Now, some of you might have actually seen this result before. This is actually known as the Gibbs phase rule. it says that if I have some number of chemical species and some number of phases, what are the conditions that still have to be satisfied? How many free parameters, temperature, pressure, and mole fractions, are adjustable such that I can keep that system at coexistence? All right, that's abstract. Let's think about what this means in a few specific cases. So let's imagine that we have a single component system. So if I have then one phase, so R is 1, V is 1, that means the number of independent parameters is still 2. So there are no mole fraction variables, so that means that the temperature and pressure can vary independently. What if I want to have two phases? That means V is 2, R is 1. I end up with F, the number of free parameters is 1. That means that T and P can no longer vary independently. I will have some solution to those set of equations that would be parameterized by T as a function of P, for example. Or if it was invertible, P as a function of T. What about three phases? That would give me a completely determined set of equations. If I have three phases, one component, that means F is 0. There's a unique solution, a given set temperature and a given pressure. So if we were to plot this in some temperature pressure diagram, if I have some phase alpha, beta, and gamma, to be in just phase alpha, there are any number of pressures and temperatures that I could visit. However, if I want to impose being in coexistence, so having two phases, say coexistence between alpha and gamma, the only way to stay in coexistence is to stay exactly on a line, P parameterized by T. Similarly, I could fall on a line if I wanted to stay in coexistence between beta and gamma, or alpha and beta. If I want to see all three of those phases, well, we've just deduced that that can only happen at a single point. There has to be a very definite temperature and pressure in order for me to actually be able to prepare and have stable all three of these phases. What if I tried to have four phases in this one component system all coexist? That can't happen. There's no way thermodynamically, if all I can vary is the temperature, pressure, and the set of mole fractions available in each phase, if I have a single component system, I don't have enough freedom to satisfy those conditions of equilibrium simultaneously. All right, well, what if I make my system a little more complicated? What if instead of a single component system, I have a binary mixture? the short story is that things get really complicated really quickly. If I have a two-phase coexistence, I would have F is 2. So I would have, say, how the fraction of these two species change with pressure and temperature. That would trace out a whole coexistence curve. So my free parameters are the temperature, the pressure, and the mole fraction. I can have coexistence over a whole domain in the temperature and mole fraction plane, say between phase alpha and beta. I could similarly have coexistence between alpha and beta along a whole constant temperature, pressure, and changing mole fraction. So this is varying amounts of phase alpha and beta. So these phase diagrams get very complicated. Nevertheless, we have, in principle, constraints that we could impose that would help guide us through this. All right, so I've already drawn 2 examples of what are known as phase diagrams. This summary of where I see different phases as functions of thermodynamic parameters like temperature and pressure. Such diagrams, not only do they tell you what you're expected to find at equilibrium under those conditions, but they contain a real wealth of additional information. Let's go through that a little bit. So let's plot a simple phase diagram, say in the temperature pressure plane between phase beta and phase alpha. So maybe there's a phase boundary, a line in the temperature and pressure plane where I'd find coexistence between these 2 phases. One thing that we immediately would know is that in the top left part of that diagram, that the chemical potential of phase beta is greater than the chemical potential of phase alpha. We know that because if we prepared beta in this part of the phase diagram, that phase diagram means that labeling alpha there means that alpha is what's stable. So we would spontaneously see the system transition from beta to alpha, which implies that that chemical potential for beta is larger than alpha. So mass spontaneously flows from beta to alpha. The opposite is true in this other part of the phase diagram. Down here where beta is stable, that means that the chemical potential for alpha is greater than that of beta. And along this line, therefore, the chemical potentials are equal. Line sets a chemical potential. The chemical potential of phase alpha is determined by the temperature and pressure. And along all of those points, the chemical potential for alpha at that temperature and pressure is equal to that for phase beta. So that is clearly true independent of what specific temperature and pressure I'm looking at. If I look at, say, T naught and P naught, that's true. At that point, the chemical potentials are equal. And if I increase the temperature a little bit, say to T naught plus delta T, if I correspondingly increase the pressure by the right amount, say P naught plus delta P, those chemical potentials are still equal. That therefore implies something about how the chemical potentials change relative to each other as I move along that line. The chemical potential for alpha and the chemical potential for beta must change by the same amount as I go from this point to that point. So to work out how much they change and what dictates that change, we need to remember, how does the chemical potential depend on temperature and pressure? So there's a thermodynamic relationship that tells us this directly, and that's the Gibbs-Duhem equation. Gibbs-Duhem says that d mu is equal to minus the entropy per particle times dt plus the volume per particle times dp. So along the coexistence line, the change in the chemical potential for alpha is equal to the change in the chemical potential for beta. I have a relationship for that change through the Gibbs-Duhem, so I could say that the minus the entropy per particle of phase alpha times dt plus the volume per particle of phase alpha times dp must be equal to that same set of quantities for phase beta. Or rearranging, we find that dp dt along the coexistence line is equal to the change in the entropy per particle over the change in the volume per particle as I go from alpha to beta. This result here is a classical result in thermodynamics. It's known as the Clausius-Clapeyron equation. Oops. So if I know that coexistence line, I know the relative changes in the entropy per particle to the volume per particle. Analogously, if I can compute independently how the entropy changes from one phase to the other and how the volume changes from one phase to another, I can predict the slope of that line. This gives us insight, for example, into why phase diagrams look the way that they do. So let's imagine comparing freezing to boiling. So if I freeze, I would take a system of particles, maybe it looks like this. Freezing means ordering those particles in a definite arrangement. The change in the entropy is typically, not always, but typically less than 0. Typically, a liquid has higher entropy than the solid. The change in the volume, however, could be positive or negative, but it's also often really small. Typically, the change in the volume is smaller, things get denser as they freeze, but that doesn't have to be the case. And even if it's not the case, it's a pretty small number usually. Now that's to be contrasted with what I get if I take this liquid and now I boil it. A rather crude way of saying I turn it into a vapor. The change in the entropy in this case is positive. I have more states available to me at those higher temperatures. The gas always has a higher entropy than the liquid. And the change in the volume is much, much greater than 0. If I take a liquid and I vaporize it, the most notable difference is that the density has changed tremendously. So that means that in the temperature pressure plane, dp dt is the ratio of entropy change to volume change. As I go from the crystal to the liquid, the entropy is a negative number, so it'll have a negative slope. All right, that is a negative number. The volume change typically also negative, so overall has a positive slope. But the volume change is typically small. So 1 over a small number is a very big number. So this slope is typically very positive, very near vertical. Whereas when I look at going from a liquid to the vapor, I have 1 over a very, very big number, both of which have the same sign. So I have a very flat slope. So in fact, that has to be the case. It always has to be the case that the slope is relatively flat and positive when you boil, and that the slope is relatively sharp, though it might be slightly positive or slightly negative when I freeze. In fact, depending on the positive or negative slope of the freezing transition, of the freezing line, you know how correlated the entropy changes are to the volume changes. A notable exception to the positive slope under freezing, of course, is water. That's a case when the density actually the density increases upon freezing, along with the corresponding increase in entropy. Density increasing means volume decreasing. That's why you have a negative correlation. Okay, so these sorts of things that we've just discussed are all examples of applying a thermodynamic framework to phase transitions, and all of these work out just fine. However, the kinds of questions that they're addressing are not why a phase transition exists. Thermodynamics is incapable of answering that sort of question. if I gave you a function, the chemical potential, and how it depends on temperature and pressure, you could predict, if I gave you that for two phases, you might be able to predict that a phase transition happens. But you couldn't tell me why that phase transition happens, because that sort of why question requires a different resolution to answer. You'd have to know why the chemical potential changes sharply, which requires an understanding of the statistical mechanics, the molecular degrees of freedom that endow that sensitivity to, say, temperature or pressure of the chemical potential. In fact, much of the phenomenology that thermodynamics and much of the phenomenology that thermodynamics attempts to understand regarding phase transitions is a bit ad hoc. Let's talk a little bit about that in the specific case of something known as a Maxwell construction. Okay. Okay, Maxwell construction. So to prelude the Maxwell construction, let's think concretely about the van der Waals gas. So van der Waals gas is a gas which obeys an equation of state for beta pressure is equal to rho minus 1 over 1 minus b times rho minus 1/2 a rho squared, where this a and b are positive constants that depend on the molecular system being considered. So there's one number for hydrogen gas, there's a different number for nitrogen gas. So this equation of state, if I were to plot it, pressure as a function of 1 over density, so that's volume, pressure versus volume has a definite negative slope, and indeed at high temperature, their van der Waals equation would look something like this, say at that temperature. If I decrease the temperature, it would look something like that. If I decrease the temperature even further, however, this van der Waals equation does something like this. And that's a problem. You all know that's a problem because, as we just stated, stability requires that changes in pressure with respect to changes in volume are necessarily negative. So this equation of state is thermodynamically inconsistent. It predicts an instability arising at low temperature. Nevertheless, if we tried to still take it seriously, one could ask, as Maxwell did, if there was anything meaningful to say about this breakdown in stability. Okay, that's a reasonable question. Let's keep that in the back of our minds. Let's now consider something slightly more generally. Let's imagine two phases, alpha and gamma, whose equations of state are known. If we have those equations of state, we can imagine using thermodynamics to integrate them and arrive at a function, the Helmholtz free energy as a function of temperature, volume, and number of particles. And we could integrate those functions for both phases. So by doing some experiments, we can infer, using thermodynamics, the Helmholtz free energy. Let little a be the Helmholtz free energy per particle. And now let's ask, what does little a look like as a function of little v? Well, how the Helmholtz free energy per particle would change with volume per particle at constant temperature is the same thing as how big A would change with big V at constant temperature and number of particles. That's just multiplying by 1, in this case 1 over n divided by 1 over n. We know that that thermodynamically is minus the pressure, which is negative for stable pressures. What about the second derivative? How A varies with V. What is the curvature of that plot? Well, that's therefore the same thing as how minus P changes with little v. Again, that is something that will then have to be positive. So if I were to plot A as a function of v, I'd have to have a negative first derivative and a positive second derivative. So let's imagine that for one of those phases, I have that. And for the other phases, I have this. Let's imagine that one is alpha, and this one is gamma. So now I can ask thermodynamically, at some given V, which phase do I see? So if I prepared the system at some specific volume per particle, specific density, which phase is likely to exist? Well, we know that the temperature of alpha and gamma have to be equal under any condition of equilibrium, and that can then just be defined as T. We know the pressure would have to be equal, so let's just define that as P. And analogously, the chemical potentials have to be equal. So the pressure is equal to how A changes with V, constant T. So that means that if they're at coexistence, so where the stability changes between alpha and gamma is a point at which A alpha and A gamma have the same slope. There's a lot of points on these two lines. A is a function of V for alpha and gamma where the slopes are the same. But since E, the energy of the system, is equal to Ts minus PV plus mu n, or A, which is E minus Ts, is minus PV plus mu n, then little a is minus P little v plus mu, dividing through by n, or rearranging mu is equal to little a plus P little v. At coexistence, so where mu alpha is equal to mu gamma, using this equation here, we know that the Helmholtz free energy for phase alpha plus the consistent pressure times the volume of phase alpha must be equal to the Helmholtz free energy for phase gamma plus the common pressure times the volume for times phase gamma. Or delta A over delta V is equal to minus P. Delta A over delta V, that's another way of saying the slope. So in fact, there is a single common tangent line which determines the coexistence between alpha and gamma. So there's a unique pressure for these curves where the stability of alpha, the phase that I'll see, changes to the stability of gamma, where I turn into conditions where gamma is favored. And that point, there's a point at which, a pressure and temperature at which those two phases will coexist. So at a given V, I might see both. So if I plot these again, ooh, I can just take this. It's such a nice drawing. Make it a little bigger. So let's say, let's label okay, so that's fine. So there's a common tangent line where that coexistence occurs. So there are many points along these lines where the slopes are similar, but there's one in which the slopes are similar and it's common, and that would be that line there. So in fact, the Helmholtz free energy observable in the system would be a line like this. We're here. So this is alpha. This is gamma. Whoop. There's a point at which that common tangent line occurred. Let's define those tangent points as V alpha and V gamma. So for V greater than V gamma. It's over on this side of that curve. Remember that common tangent line denotes the condition for coexistence. So if I'm at larger V's than V gamma, that implies that mu alpha is greater than mu gamma. And so for those volumes, gamma is the stable state. By contrast, for V less than V alpha, the location of that tangent line, alpha is stable. What does it mean if we have a volume in between V alpha and V gamma? So that whole line, that common tangent, is a whole line of coexistence points. So there we have both alpha and gamma. We have a coexistent mixture of the two. So again, by knowing these equations of state, inferring the Helmholtz free energy as a function of volume, and imposing the conditions of equilibrium, that the chemical potentials and pressures are the same, we have inferred, given those equations of state, which state we're likely to find, alpha or gamma, depending on what volume we set. And curiously found that there's a point at which, or a set of points, a set of volumes, over which neither one is dominant over the other, rather we find a coexistent mixture between the two. So we took this little detour, having started with the van der Waals equation of state. What does this imply for the van der Waals equation of state? So we found that under certain temperatures, P is a function of 1 over rho, which is the same as what we've just called little v, has this inflection. If P is minus dA d little v, A at V2 minus A of V1 is then the integral of V1 to V2 dV P of little v. So if I was to integrate the plot on the left, I would get something like that over on the right. That looks very much like those two independent branches of alpha and gamma for the Helmholtz free energy. And indeed, there is a location on this curve where there's a common tangent. Those points there. And we can essentially try to repair that instability by invoking the coexistence of those two phases. So if we imagine that what the van der Waals equation of state is telling us, that there is essentially, it's trying to describe both a liquid and a vapor, that instability we notice in pressure is really saying that there are two branches of solutions of that van der Waals equation, indicating solutions for high volume, the gas, and low volume, which is imagined to be the liquid. We can make that slightly sharper by noting that, of course, at coexistence, P liquid is equal to P vapor, which is equal to some P. And from our discussion above, A liquid at some liquid volume plus P times that liquid volume must be equal to A vapor at its volume plus P V vapor. That's a way of expressing or stating the equivalence of the chemical potentials. Again, this is some delta A, which is equal to P times some delta V. Delta A, as we've just described up here, can be computed by the equation of state P of V, integrated from V vapor to V liquid. From the right-hand side of this above equation, that's a constant pressure, some coexistence pressure, integrated over some volume V vapor to V liquid. That's a fancy way of writing delta V. That equivalence has a geometric interpretation. Minus P times the integral dV, that's the area under a line at constant pressure. The left-hand side is the area under the curve P of V. Where those two are equal is where you have coexistence. So if we plotted this now in the pressure volume plot, so we had something like this. So if we were interpreting this instability as locating coexistence between some vapor state and some liquid state, coexistence means the liquid and vapor have the same pressure. There's a number of different lines I could draw, and the equation above says that there's a unique line such that these integrals are the same. So that denotes some coexistence pressure. So this is known as a so-called Maxwell construction, or an equal area construction. So rather than allowing that instability to persist, one cuts it off by imposing coexistence. All right, so this is and kind of ad hoc fix Maxwell imposed to work around the difficulties that thermodynamics has with phase transitions, that phase transitions are these sharp changes, these apparent instabilities that arise as a phase transforms between one state and another. It's not super satisfying. There are good reasons to think through why this is kind of ad hoc, and reasonable to ask why it should not work, but nevertheless it is a pragmatic approach. It fixes a thermodynamically inconsistent equation of state and imposes thermodynamic consistency. So there's at least that. So you'll have some exposure to these sorts of equal area constructions in one of your upcoming problem sets. It won't be of a gas, but you'll consider it in a slightly different context. Okay, so stay tuned. In the next couple lectures, we're going to try to summarize all the things that are wrong with thermodynamics as applied to phase transitions and a set of paradoxes that arise when you start thinking about thermodynamics and phase transitions. And that will put us in a strong position to then go forward and start developing this more microscopic perspective. Okay, so stay tuned for all that, and I'll look forward to seeing you all in the live session.